Alright, so in this video, we're going to be talking about the scalar triple product, okay? And this is actually something that came up in our properties of the cross product video. We saw that, the product of vector A dot, in parentheses here, B cross C could also be written as A cross B in parentheses dot C. Okay, those two things are equal. But anyways, in this video, we're actually going to be talking about the purpose of this. And this thing right here is called the scalar triple product. Okay. Now we're bringing up something new, so there's obviously got to be some applications of this. There's got to be some purpose of why we're learning this. And there's two main reasons that we're learning this that we're going to go over in this video. Okay. The first is to find the volume of a 3D parallelogram, and that's called a parallelepiped. Okay, it's a really weird name. Anyways, so you see here that this 3D parallelogram here, don't mind this red vector here, is basically defined by vector A going up here, vector B going across, and vector C kind of as the depth, okay? And now, basically, we need to figure out what the volume of this parallelepiped is, okay? So first, we can figure out the area. The area, we'll just find the area of the base. We do that, right, and we know this, the area of a parallelogram, which is going to be this parallelogram defined by B cross C. It's the base of this 3D parallelogram, okay? The area of that is going to be B cross C. Okay, we did that. If you're not sure where I'm getting that from, definitely go check out my video on just more uses of the cross product, or I believe it was just titled the uses of the cross product, whatever. But anyways, yeah, volume equals B cross C. Now we still need to multiply that by the height, okay? And, well, first off, actually, before we continue here, is it going to be B cross C or the magnitude of B cross C? Okay, that's actually something important that I didn't write down there, okay? Now, we want the magnitude of B cross C because the volume is going to be a scalar quantity. Okay, we can't just put a vector in here. Okay, we got to find the magnitude of it. Think when you find the volume of something, let's say you're finding the volume of a cube, length times width times height. You're not putting in vectors, you're putting in numbers like 3, 4, 5 or something like that. Okay, so it's important to put that down. Now the height. Okay, the height is basically this distance right here. It's the distance from. See if I can write a curly bracket here. Oh, did it? All right. So it's this distance right here, okay? And basically that's this from this point to this point on this red line, this vector that's B cross C, okay? Now the length of that vector is the area of this parallelogram. Okay, we've already been through that. But up to this point right here, okay, that length is going to be, it's going to be A cosine theta. Okay, and we're actually going to have to take the magnitude of that, but this is going to be the magnitude of A times the absolute value of cosine theta. Okay, why is it the absolute value of cosine theta? Well, if theta is greater than pi over 2, you're going to need to have that absolute value there, because you might get something negative out of that cosine theta. Okay, and how do you know, am I supposed to be taking the magnitude of this or not? Well, this isn't a vector. Okay, you take the magnitude of a vector, and you find the absolute value of a scalar. Okay, so how do I know that this is the same thing as the magnitude of A times cosine theta? Well, if I flip it like this, it might be a little easier to see. So let me go ahead and do that. This vector right here is going to be B cross C. Okay, and then we'll have vector A up like this. Okay, and then the angle right here is going to be theta. Now what we can do from here to figure out how we got this magnitude of A times the absolute value of cosine theta, we can just find cosine theta here. Okay, cosine theta is equal to the adjacent side over the hypotenuse side. Okay, and the adjacent side to this triangle, okay, you can make a triangle here. The adjacent side is B cross C. Okay, so this is equal to B cross C, and that's going to be over your hypotenuse, which is your vector A. Now, we need to find the magnitude of these vectors. Okay? Again, think about it. When you were finding this maybe in trigonometry, algebra 2, whatever it is now, okay, you didn't put in vectors into the adjacent and your hypotenuse, okay? You put scalars, okay? We're talking about lengths here. So we find the magnitude of B cross C, we find the magnitude of vector A, okay? And so if this is equal to cosine theta, then if we multiply by the magnitude of A on both sides, you can see that we get cosine theta times the magnitude of A is equal to the magnitude of B cross C, okay? Now we can simplify this down further because we know that cosine theta, that equals A dot B over the magnitude of A times the magnitude of B. Okay, that's something we learned when we talked about the dot product. Now, we have a magnitude of A times cosine theta over here in our volume equation. So, if we multiply here by the magnitude of A, then what we get is the magnitude of A times cosine theta equals A dot B over the magnitude of B. Now, B is just going to be any vector here, okay? I guess I could have used different variables here, but don't associate this B with this B over here, okay? These are not going to be the same vectors, okay? This is just a different kind of example over here, okay? B can just be any vector, okay? B cross C is a vector, okay? The cross product is a vector. So what I can do here, okay, is I can say that the magnitude of A times cosine theta is equal to vector A dot, we're going to plug in B cross C for this B right here, okay? And we're going to put that over the magnitude of B cross C. And we can do that, okay? This is something that we're able to do. Like I said, B can be any vector, okay? And don't associate it with the B over here, okay? I could say the vector E right here. I could say vector E, okay? If that helps at all, I'll put E right here and E right here, okay? What I mean is that it can be any vector, okay? And B cross C is going to be the vector that we plug in, all right? And, well, that means that we have that this portion right here, this magnitude of A times cosine theta, is equal to the vector A dot your cross product of B and C is going to be over the magnitude of B cross C. So when you plug that in, you get that the volume is equal to, we're going to keep this right here, this B cross C, okay? And then this magnitude of A times the absolute value of cosine theta is going to become, well, this is going to be A dot B cross C over the magnitude of B cross C. The magnitude of B cross C cancels out, and you're just left with that the volume is equal to the not magnitude, just the vector A dot B cross C. Okay, so the volume of a parallel pipe head is literally your scalar triple product. Okay? Now, there is also, and I'm going to be doing example problems with this stuff in the next video, but there's also another big use that we're going to be talking about in this video. Now, the second use of the scalar triple product is to find out if all of your vectors share a plane. Okay? If they all share a plane, what they're called is coplanar. Okay? So trying to figure out if all of your vectors are coplanar. Okay? Now, your vectors are coplanar if your scalar triple product equals 0. Okay? And think about it, okay? I'm going to bring back up this parallelepiped, okay? If your scalar triple product is 0, that means that the volume of this parallelepiped is 0, okay? And assuming that you don't have some 0 vector in here, what that means is that either your dot product is 0 or your cross product is 0, okay? Now, if your cross product is 0, okay? If your cross product right here, if B cross Z is 0, what that means is that B and C are parallel, okay? If they're parallel, well, that means that you don't have any of that depth dimension anymore, and this thing becomes, assuming that A points in a different direction, it becomes two-dimensional, okay? And if it's two-dimensional, you can fit all those vectors on one plane, okay? Therefore, your vectors are coplanar. And of course, if this is 0, okay, A dot 0 is going to be 0. So you get that your scalar triple product is 0. Now, what if this B cross C by itself isn't 0? What if having A dot this is what ends up making this whole thing 0? Okay, not the cross product itself. Well, what that would end up meaning is that A is perpendicular to this vector B cross C. Okay, and B cross C, well, that points upward. Okay, that's orthogonal to both B and C. So if A is orthogonal to B cross C, well, that means that it's on the same plane as C and B. Okay, you would have your A going out somewhere in this plane. Okay, the base of the parallelepiped, that would become your plane. Okay, and again, your vectors would be coplanar. Okay, so that's the whole idea here. Okay, your angle between B cross C and A would be 90 degrees, and that would push your vector A down to B and C. Okay, so that's the two main uses, okay, to find the volume of a parallelepiped and to see if your vectors are coplanar. Now, me personally, the questions that I've gotten has always been coplanar and not the volume of a parallelepiped, but maybe you would end up trying to find this volume, okay? But I'm just saying that most of the questions I've got have been on if vectors are coplanar or not, okay? So we're going to be doing practice problems in the next video, so I'll see you then. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for vectors and the geometry of space in the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.